When a utility provides an infinite short circuit MVA value and there is a transformer downstream, the short circuit value at the secondary of the transformer is reduced. This reduction is proportional to the transformer's turns ratio. To calculate the short circuit MVA at the secondary, you need to understand the turns ratio and the base MVA. In the example given, the transformer has a primary voltage of 11,000 volts and a secondary voltage of 3,300 volts. This results in a turns ratio of 11,000 volts divided by 3,300 volts, which equals 3.333. This means the short circuit MVA at the secondary of the transformer will be reduced by a factor of 3.333. To determine the short circuit MVA at the secondary, divide the infinite MVA from the utility by the turns ratio. Therefore, infinite MVA divided by 3.333 equals 3000 MVA. Next, to calculate the short circuit current at the secondary of the transformer, you use the following formula: short circuit MVA divided by the product of the secondary voltage and the square root of 3. In this case, 3000 MVA divided by 3,300 volts multiplied by the square root of 3 yields 5.77 kiloamps. Note that these calculations are theoretical. In practice, the actual short circuit MVA at the secondary of the transformer may differ slightly. This difference is due to factors such as the transformer's impedance and the impedance of other components in the circuit. Transformer impedance plays a critical role in limiting fault currents. The higher the impedance, the lower the fault current. Transformer impedance is typically expressed as a percentage of the transformer's kVA rating. For example, a transformer with an impedance of 6% will limit the fault current to approximately 16.67 times the transformer's full load current. To calculate the fault current, you must first determine the transformer's full load current. The formula for calculating the full load current of a three-phase transformer is kVA divided by volts multiplied by the square root of 3. Once you have calculated the full load current, you can calculate the fault current by dividing the full load current by the transformer's impedance expressed as a decimal. For example, if the transformer has a full load current of 100 amps and an impedance of 6% or 0.6, the fault current would be 100 amps divided by 0.6, which equals 1667 amps. Several factors can affect the short circuit current, including the source impedance, transformer impedance, cable impedance, and motor contribution. Source impedance is the impedance of the utility's power system. The higher the source impedance, the lower the fault current. Transformer impedance is the impedance of the transformer itself, as previously discussed. Cable impedance is the impedance of the cables connecting the transformer to the load. The longer the cables, the higher the impedance and the lower the fault current. Motor contribution refers to the current that motors can contribute to a fault. When a fault occurs, motors will act as generators and feed current back into the fault. This motor contribution can increase the fault current significantly. Short circuit studies are essential for ensuring the safety and reliability of electrical power systems. These studies help engineers determine the magnitude of fault currents that can occur in a system and to select appropriate protective devices such as circuit breakers and fuses. Protective devices are designed to interrupt fault currents quickly and safely, preventing damage to equipment and injury to personnel. A short circuit study typically involves modeling the power system using specialized software. The software calculates the fault currents at various points in the system under different fault conditions. The results of the short circuit study are then used to select appropriate protective devices and to coordinate their settings. Coordination of protective devices is crucial to ensure that the device closest to the fault will operate first, minimizing the impact of the fault on the rest of the system. There are several standards and guidelines that govern short circuit studies, including the Institute of Electrical and Electronics Engineers, or IEE Standard 141, which provides recommended practices for power system analysis, and the National Electrical Code, or NEC, which provides requirements for the installation and protection of electrical systems. When performing a short circuit study, it is important to consider all potential fault locations, including faults on the primary side of the transformer, faults on the secondary side of the transformer, and faults on the load side of the transformer. It is also important to consider different types of faults, such as three-phase faults, line-to-line faults, and line-to-ground faults. Three-phase faults are the most severe type of fault and involve all three phases of the power system. Line-to-line faults involve two phases of the power system. Line-to-ground faults involve one phase of the power system and ground. The magnitude of the fault current will vary depending on the type of fault and the location of the fault. In addition to calculating fault currents, short circuit studies can also be used to determine the voltage drop during a fault. Voltage drop can cause equipment to malfunction or shut down. It is important to ensure that the voltage drop during a fault does not exceed acceptable limits. To mitigate the effects of short circuits, several measures can be taken, including using current-limiting reactors, using high-impedance transformers, and improving grounding systems. Current-limiting reactors are devices that are installed in series with the power system to limit the fault current. High-impedance transformers have a higher impedance than standard transformers, which helps to limit the fault current. Improving grounding systems can help to reduce the magnitude of ground faults. Grounding systems provide a lower impedance path for fault current to flow back to the source, which helps to trip protective devices quickly. Proper grounding is essential for the safety and reliability of electrical power systems. It is important to ensure that all equipment is properly grounded and that the grounding system is regularly inspected and maintained. In summary, understanding short circuit calculations is essential for electrical engineers and technicians. By understanding the factors that affect fault currents and by performing short circuit studies, engineers can design and maintain safe and reliable electrical power systems. Remember to consider the turns ratio, impedance, and potential fault locations when performing these calculations. Protective devices like fuses and circuit breakers are crucial to protect your systems in the event of a short circuit. Regular maintenance and inspection are also important,